5,000-pound thrust engine at the time, a huge market would open up in front of him. But he needed a partner. And the example of Concorde told him that the partner had to come from the US. So what he did, he crossed the Atlantic and he went to meet this gentleman here, who was the CEO of GE Aviation at the time. And the two of them, his name was Garrett Newton, because you might think, if no one is really the leader, then you have to compromise all the time. Doesn't sound very efficient. But if you have one with 49, that one is always frustrated, so it doesn't work. The 50-50 is very important. And we have all processes at Safran and GE and CFM to make things work pretty easily. So everything is shared 50-50. The engine that you see here, shared 50-50. GE does the core, Safran the low pressure system. We share sales, design, development, production, 50-50. Even modestly, we split the world 50-50 for sales and customer support. Everything in blue here is covered by GE, and everything in red is covered by Safran. The other key factor of success, in my opinion, is that we never talk about cost. Never talk about cost. The chances back in the 70s that the cost structure of a company like GE listed in the stock exchange and a company like Stegma, state-owned, were different, was pretty high. So what we do is, anytime we receive $1 from a customer, we split it 50-50. So for the engine, for instance, every part of the engine is given a percentage as a relative value of a total. And we make sure that both partners do 50% and 50%, and then we split the revenue. We never talk about cost. So those, in my opinion, so we have three ranges of products and services. The CFM56, well-known engine, we have delivered nearly 34,000 of them. When you imagine that the program was just about to be cancelled back in 1979 because the two founding fathers were unable to receive an order. They developed a brand new engine and had no orders, and the first order came just 2 weeks prior to the official cancellation day. 34,000 engine. Thank God they really, had this vision and hang on their vision. We're still producing a few engines there to serve the spare engine market, as well as a military program we have with Boeing called the P-8 aircraft. The LEAP, which was launched in 2008 and entered into service in 2016, we have sold more than 20,000 of those engines, orders and commitments, and have already delivered more than 5,000 of them. So the engines on the LEAP-1A for Airbus, LEAP-1B for Boeing, and LEAP-1C for Collide. And in the middle here, in 2008, the two parents decided that the partnership would be extended to services. And so CFM provides a whole range of services, maintenance, overall, all sorts of flexible solutions to airlines and operators around the world. And we have now more than 150 customers which are under CFM services contracts. Next chart is Kevin.
Thank you, Gak. There we go. Got it. So, as Gael said there, transitioning to a little bit more of numbers. 50,000 total CFM56 and LEAP engine orders. We've got a long history, but we also have a long way to go. Those engines have contributed over 1.2 billion cumulative engine flight hours. This third stat here I think is probably the most interesting. Of all aircraft with over 100 passengers, 55% of those are powered by CFM. So that includes wide bodies, and CFM is not on wide body aircraft. Another reference point there is that roughly 60% of all NEOs are powered by our LEAP-1A engine. There's been 40,000 CFM56 and LEAP engines delivered to date, with 3 current applications. The LEAP-1A is on the A320neo family, the LEAP-1B is on the 737 MAX family, and the recently certified COMAC C919 has our LEAP-1C engine. Next slide, please. Okay, CFM within Latin America. As Gael said, there's a long history between GE and SNECMA in relation to CFM, but there's also a long history with CFM within the region of Latin America. Next slide, please. Okay, if I go back to 1988, Conviasa introduced the CFM56-3 on the 737-300. Another critical date for the region was the plant at GE Selma in Brazil. This plant is a world-class shop servicing all types of CFM56 and LEAP engines. Moving forward, Dole introduced the first 7B powered NG roughly 25 years ago, with still NGs within their fleet. Interjet was the first 5B operator on the A320ceo. Safran opened a shop in Mexico approximately 15 years ago, which serves CFM56 engines and is transitioning to LEAPs as well. And if I look forward to the current generation of NEOs and MAXs, Azul was the first operator of the NEO with LEAP-1A power in the region, and Aerolíneas was the first of LEAP-1B power on the 737 MAX. We've had a long history in this region and have a long way to go as well. There are numerous operators, if we go to the next slide, who are powered by the LEAP-1A and LEAP-1B. Next slide, please. So on the left side there, you've got Avianca, Azul, Sky, and Viva Colombia. On the right side, Aerolíneas, Aeromexico, our most recent add to the family, Aerojet, Caribbean, Cayman, Copa, and Gold. As you can see, there's a variety of operators from ULC to full service carriers here on both sides of the page. We're very proud of the variety of customers that we have within the region and look forward to things to come, not only with these customers, but with additional customers as well. Next slide, please. So what's next? Gael?
Yes, so what's next for CFM? Well, developing an engine takes time. Just to give you a reference, the LEAP engine that we see flying today has beautiful fan blades, composite fan blades. Those fan blades, Safran started to work on those fan blades in 1998 for an entry into service in 2016. So we have to be always ahead of the game. And the big situation of aviation right now is sustainability. We as an industry have committed, and it was last year in Boston at the IATA General Assembly, to be net zero carbon by 2050. That's the goal that we set ourselves. Very ambitious goal. And CFM has to contribute to that goal because CFM is the #1 engine manufacturer in the world. And so we are currently working on a development, maturation and acquisition technical program called RISE. Next chart. It's supposed to be a nice, powerful music. So to imagine.
You got the microphone, you can sing.
I can sing, yeah. No, it would be terrible. All right, so next chart. RISE. So what RISE means? It's revolutionary innovations for sustainable engines. It's a program that for which the partners suffer. Here comes the music. That makes sense. So the next chart will give us, yeah, there you go. So we have set ourselves the goal to come up in the middle of the next decade, which is when the next generation of engine should theoretically arrive, with an engine that will be 20% better in performance compared to the best engines today. 20% better in performance, and therefore in fuel, and therefore in CO2 emission. How are we going to achieve that? Well, we have to create a step change in propulsive efficiency. And to create a step change, we have to change the architecture of the engine. And so brace yourself. This is the kind of engine that will be flying in the next decade, in the middle of the next decade. We are used today to see engines with a fan encapsulated into a nacelle. And those engines lead to what we call bypass ratios between 6 for the CFM, 10 to 12 for the LEAP. By removing the fan cowlings around the fan like this, by growing this fan into 4 meters in diameter, we are able to achieve bypass ratio of more than 50, just to give you the idea of the step change. So a propulsive efficiency step change. There will be also a new compact core that will yield extremely high pressures for more performance, with new materials like the CFCs, for instance, composite matrix ceramics, which are incredible material because they are 1/3 the weight of a comparable metallic part, but they have twice the strength and they resist to temperature, 20% higher temperatures, CNCs. This engine will be hybrid electric. We have, as a matter of fact, started testing, which are very encouraging in bringing this hybrid electric capability to the engine. Additive manufacturing, both CFM partners have specific plans to make those parts, which are providing an incredible improvement in terms of weight and resistance. This engine will be 100% compatible with sustainable aviation fuel and possibly also hydrogen. I'll come back on that. We currently have more than 1,000 engineers working on this RISE program, and we are adding more and more every week. We're working on 300 separate built-in test plan on 150 vehicles. And again, as I said, the goal is to bring this step change engine into the market in the middle of next decade. Next chart. And before that, we will show 2 demonstration programs. The first one is the open fan demonstrator. So you see the open fan I was talking about. We are currently designing a demonstrator that we fly on an airplane. Here it's on an Airbus A380. Because we partnered with Airbus, we announced it in Farnborough. We are going to test together with Airbus the open fan engine on the A380 to check the interaction between the wing and the engine, verify all the aerodynamics, make sure that the performance we're looking for are here, and check on the behavior of the engine, because obviously this type of engine has to have at least the same or even better, I would say, cabin comfort for the passenger as today's turbofan engines. It's not a propeller engine, it's a turbofan engine, like the one you know today, except there's no cowling around the propeller. So that's one. And so that flight test should happen in the middle of this decade. So hopefully in Farnborough or Le Bourget, in the middle of this decade, we'll be seeing an airplane flying with the open fan. We're working hard to meet that commitment. And the other one is an hydrogen demonstrator. Hydrogen is a very fascinating fuel for aviation. It's not an easy one. There are difficulties, but it's a true zero carbon emission fuel. If you burn fuel to propel an airplane, there will be zero carbon emissions. And so in order to check how we can make this happen, we have teamed with Airbus, and we announced it earlier this year. Airbus will provide an A380 test bed and will fit the aircraft with 4 hydrogen tanks, and will design the system and produce the system that will bring the hydrogen to the engine in the form of liquid hydrogen. Then the engine, at the engine level, will turn this liquid hydrogen into a gas that can burn in the combustion chamber. We at CFM will provide what we call a passport engine. It's a G engine, smaller than the LEAP. The reason why we wanted it like this is because you see here, the engine will be mounted on the fuselage, of the plane. Because if we had put the engine at the place of one of the existing engines, it would have been very difficult for the chasing plane to measure the emissions, the contrails, all what we want to see. So we put the engine on top of the fuselage so that we won't have to mess up with the other engines. And because of the structural strength for the pilot here, a passport engine was making more sense than the LEAP, which is a bigger engine. And so we'll test this engine working on hydrogen in the middle of this decade. So I think that's our last chart. CFM, so from 1971 to 2035 and 2050 for the net zero carbon goal. And Kevin and myself are open to any questions you may have.
Yeah, absolutely. I have presents I forgot to put out, by the way. The other thing is, if you would like a PDF copy of all of these charts, I'm happy to send them to you. Oh,
Here you go.
okay. Sorry. If anyone would like a PDF presentation, copy of this full presentation, just give me your business card and I will send it to you in just a few minutes. Are there any questions?
Thank you. Question from Economic. It is just a question regarding the current engines that we have. We're talking about SAF here in the event today, and we have engines that are capable of operating with 50% of SAF. But recently I've been talking to some CEOs from airlines, and they were saying that despite being capable of operating with 50%, we don't have much data about the time on wing of those engines, and which causes them they are kind of afraid because they don't know how likely this engine is supposed to go to an intense in the future. So it's kind of a lot of doubts about cost operation. And do you have any numbers you can share about this topic?
The only thing I can say is that as far as we are concerned, the CFM 56 engine and the LEAP engine are fully capable of flying with SAF. We have demonstrated it. We started on the CFM 56 back in 2006, and you're right, today the regulation imposes a maximum blend of 50% SAF, 50% jet fuel. We're really pushing hard to increase that ratio all the way to 100%, because all the tests we've done so far show that, I mean, I've been myself flying an airplane. It was a United flight from Chicago to Washington, D.C. When was that? Last year in November, December 1st last year. And so the engine performed exactly the same way. There's no difference. And so we need now to feed more and more data to the authorities. It's fair. They want to be convinced. This is our job. And my opinion, we'll see this ratio increasing. And the fact is that today the availability of SAF is not it's kind of difficult, because existing SAF production covers less than 1% of all commercial aviation need. But there is a whole movement of SAF production, and this number is going to increase and will in parallel increase the blend ratio. So for my answer to your question is, we don't see any reservation in using SAF on our engines.
But in terms of time only, it's just a very specific one, but some CEOs were telling me that normally an engine stays for 6 years until going to a maintenance for the first time. Do you have any data on?
There's no reason why it wouldn't be the same. I mean, the way all the tests we've done are showing that the engines are behaving the same way, whether it's SAF or whether it's jet fuel. Actually, the thing is, you have to remember that SAF is the same as jet fuel. Eventually, when it comes into the combustion chamber, it's the same as jet fuel. It's the way it's processed that is sustainable.
Oh. He's gonna ask in Spanish.
Okay.
Eu vou fazer a minha pergunta em português para não perder a raciocínio e já peço desculpa pela tradutora. Não? Então, me desculpe pelo portunhol. Há poucos dias atrás, tivemos o cancelamento de Rolls-Royce em motor supersônico. E outros fabricantes de motores não mostraram interesse para continuar nesse projeto. O que se fala foi a respeito de motores econômicos, motores que não poluem, mas não se fala mais em supersônico. Não voaremos mais supersônico? Qual é a barreira? Física, aerodinâmica, financeira, todas elas. Gracias.
Well,
Repeat the question, please.
so the question is, why are engine manufacturers not more interested in supersonic flying, supersonic engines? Giving the example that Rolls-Royce just bailed out of a project. I can only speak for CFM, and I will just speak for CFM. You are totally right. What we are focusing now is to develop an engine that will be a step change in emissions and performance, fuel performance, compared to today's engine. And this requires an enormous amount of investment from both parent companies. Is there a market for supersonic? Maybe, but at least at CFM, we don't see that market significant enough for us to divert our current investment for sustainable engines like that into a supersonic engine. I'm sure that there might be interest by other manufacturers, I don't know, but when it comes to CFM, this RISE program represents a huge investment. We are committed to do it full speed with no restrictions, but this doesn't open much opportunity to do something else, especially when we talk about potentially niche market.
One more question.
Growing Government Flight Global. It's just a simple one, really. Obviously, we had the long-term aspirational goal at ICAO last week. Does that change anything for you, or what do you think that might do to kind of fast forward things?
I don't think so. I think we're right into where all this industry wants to go. You know, today, and it's a fact, commercial aviation represents 2% of all man-made CO2 emissions. 2%. Doesn't sound a lot, right? And I often say, even if with a magic wand we were able to erase those 2%, humanity would still have to deal with 98%. But these 2%, we're committed to bring them to zero, and we will. It's going to take a little time. The first step is sustainable aviation fuel, because it's a quick win. Then technology will come into place, and by the middle of next decade, we'll be flying engines which are considerably better in performance and in CO2 emissions. And coupled with SAF, coupled with even hydrogen, we will altogether reach the 2050 goal. So for us, all these long-term commitments that the aviation industry is taking falls well within our strategy. We are the world leader in aircraft engines, and we will show the pace, the way towards decarbonation of the industry.
Great, I think we are about to lose the room, so thank you all for your time. Do you have a question?
And last one?
And again, if you do want a PDF version of the presentation, just give me your business card and I'll send it to you in a few minutes.
Gracias. Me gustaría saber si la implementación de estas nuevas tecnologías y los motores va a requerir capacitación para el personal técnico y de mantenimiento de las aerolíneas.
So, despite this engine very different compared to what we see today, the basics are the same. So it's a fan with a compressor and turbines. So the whole principle is the same, and therefore for maintenance people and everything, it shouldn't be completely new and difficult to adjust. There will be new material, the size of the core will be smaller, but like we do for all CFM engines, we'll make sure that all the line replaceable units will be accessible. We are working with the airframers right now to decide where is the best place to put this engine, because we could put it at the back of the plane also, but when we do that, the engine is very high and it's more difficult for the maintenance, on-wing maintenance people to access the engine, so we have to weigh all the options. But no, especially by 2035, I mean, every airline will be able to step into this program and ensure the maintenance as they are doing today.
And if I could interject one more data point, the size of the fan is equal to engines that are flying on wide-body aircraft today. So airport facilities don't have to be changed to accommodate an open fan engine.
Thank you very much for your attention. Thank you so much.